Welcome back to Sports and Building Aerodynamics, the week on wind tunnel testing. This module we're going to focus on wind tunnel components. Let's start with the module question. The honeycomb is an instrument that is used in a wind tunnel before the contraction, so before the actual test section. And an example is shown here in this picture. What is the effect of a honeycomb on the flow through this device? Do you think that A, it increases the turbulence intensity in the direction of the flow? B, it decreases the turbulence intensity in the direction of the flow? Or C, it increases turbulence intensity in the direction perpendicular to the flow? Or the final answer, D, decreasing turbulence intensity in the direction perpendicular to the flow? Please hang on to your answer, and again, we'll come back to this in the rest of this module. At the end of this module, you will understand the position of different wind tunnel components and their function and purpose. So let's now take a walk around the wind tunnel, through a wind tunnel, and we will discuss every component as we encounter it. And later we'll focus in more detail on the exact function and purpose of each component. This is an example of an atmospheric boundary layer wind tunnel, the ABL wind tunnel at Université de Liège in Belgium, with a test section of 2.5 by 1.8 square meter. Here you see the flow direction indicated. Now I have to mention that the photographs that I will show later on are not necessarily those from this wind tunnel. I've just selected those two for maximum clarity of presentation. So we start here at the location of the fan and the flow straighteners. And the intention of these devices is, of course, to drive the flow, but also to remove the swirl generated by the fan. Then we move down the diffuser, which is used actually to increase the cross section and to reduce pressure losses. Then we go around the corner, and therefore corner vanes are used to change the flow direction with the minimum in pressure losses. Then there's a wide-angle diffuser, and that actually is intended to increase the cross section to install the screens in the honeycomb. Then we have the settling chamber that contains those screens and honeycomb. Then there is a honeycomb, which is intended to reduce differences in transverse and vertical turbulence intensity over the cross section. Then there is some screens, usually more of them, intended to reduce differences in longitudinal velocity across the cross section. Then there is a contraction, which is further intended to reduce turbulence intensity, but also to align the flow and to speed up the flow. And then finally, you have the test section, which, for an atmospheric boundary layer, has to be equipped with the appropriate roughness features, as we discussed in the previous module. And these consist of spires and barriers and roughness elements. And then finally, just before the fan, we have to install a safety screen, because in case the model would fail, we would not like to damage our fan. Okay, let's now go a bit more in detail on the function and purpose of each of these components. And there are two ways to do this. There is many textbooks that provide excellent information on the equations for different pressure losses by different components. This is what I'm not going to show you in this MOOC. Actually, here we're going to take a more phenomenological approach, and therefore not less scientific. For a textbook, indeed, the first approach might be preferred, and you can find a lot of valuable information there about pressure losses. But for the MOOC, maybe it's more illustrative to take the second one. First, the fan and flow straighteners. It's a unit that includes the fan nacelle, then the fan, of course, itself with the fan blades, and then either pre-rotation vanes or flow straighteners together with the fan. So what is the purpose here? Well, the purpose is to take the incoming airstream, which is usually uniform, and then convert it to an outgoing stream with a larger static pressure, and that is also as uniform as possible. The pre-rotation vanes, or the flow straighteners, actually are meant to reduce the swirl in the flow, because indeed the fan generates quite some swirl, and this is unwanted in the remainder of the wind tunnel. Pre-rotation vanes are not that often used in atmospheric boundary layer wind tunnels. Usually you will see flow straighteners being applied. And here in this graph you see the fan blades in black, and you see the flow straighteners in orange indicated. The fan and, of course, then also the flow straighteners should be located preferably downstream of the second corner, and that is counting from the test section. And that is because the fan is most efficient in a region of an airstream with a high velocity, but also a uniform stream, and in a place where you can reduce the cost by a lower, smaller diameter. Then the purpose of the fan, of course, is to increase the total pressure and actually to balance the pressure loss that you will have in all the other components of the tunnel. And that is schematically indicated here. So how do you choose the fan? Well, this is done with the method of characteristic lines. So there is a system curve, which is the curve that gives a relationship between the pressure loss and the flow rate in all the different components. And then you have to match the fan curve with that and find a suitable working point of operation. Okay, let's then move to the diffuser. The intention of the diffuser is to increase the cross-section, and it should have a small angle to avoid flow separation, because if you have flow separation, we will lose energy and we will disturb the flow in the wind tunnel, which is clearly unwanted. So here, indeed, by increasing the cross-section, we reduce the wind speed and we increase the pressure. So this is indeed a tool for pressure recovery. And you can show that very simply if you go back to the Bernoulli equation along a streamline that we discussed in the first week, then you can write it in this way. And if we have a horizontal streamline, well, then the height does not play a role here. And then we can easily show by some simple algebra that indeed when the cross-section increases, that also your static pressure increases. So indeed, we have pressure recovery. Then there's the settling chamber that contains the screens and the honeycombs. It has a large cross-section. We want to make that as large as possible in order to minimize the pressure loss due to the screens and the honeycombs, because the higher the velocity through those devices, the higher the pressure losses will be. So the function of this settling chamber with the included screens and honeycombs is really to reduce drastically the turbulence intensity and to straighten the flow. Then we have the corners, of course, and in the corners we put corner vanes that can have different shapes and sizes and different spacings between them. Well, the specifications are in the corners, of course, that's logical, but mainly they're vertical. They're also made aerodynamic, can simply be bent plates, but can also be highly cambered airfoils, and they have a pivoting option that allows you to carefully align them with the flow. So they're really needed to avoid large pressure losses that we would otherwise have in the corners, and to ensure a uniform and straight flow around this corner. Then there's a honeycomb. Usually the cells of these honeycombs are round or square or hexagonal. They have a diameter of 5 to 10 millimeters, and the length is about 10 times the diameter. Porosity is quite large here, and the function is to straighten the flow. The function is, as indicated in this drawing, to reduce the turbulence intensities perpendicular to the flow direction. So indeed, as shown here, we want to break up the vortical structures into much smaller vortices, and actually this way to reduce turbulence intensity, but also to align the flow. Then there is the screens. The wire diameter of screens is often only 0.04 to 0.5 millimeters. Porosity is less than with honeycomb. The function here is actually to reduce the streamwise turbulence intensity, so to even out velocity differences, and that works because the higher the velocity, the larger the pressure loss will be. So this actually works as equalizing the velocity across the cross-section, so the streamwise velocity. Then there's the contraction. Contraction ratios can vary between 2 and 20, but usually they're about 4 up to about 8 for ABL wind tunnels. And their function is to reduce turbulence intensities in all directions, actually, and to align the flow, but also to increase the mean wind speed as we are actually providing the flow for the test section. And then there's a test section, of course, where we have generally a long Fedtchen atmospheric boundary layer wind tunnel with the earlier discussed roughness features, the spires, the barriers, the roughness elements, and there we want to establish the right ABL profiles. And then also in this test section, we should have an adjustable ceiling to ensure that we have a zero or a near zero longitudinal pressure gradient. And finally, the test section itself, which consists of a turntable that can be rotated to change the wind direction, change orientation of the model. The blockage ratio here should be lower than 5%. The function is, of course, to perform the actual measurements, and then we can turn back to our module question. What was the effect, or what is the effect of a honeycomb on the flow through this device? Well, it mainly acts on decreasing turbulence intensity in the direction perpendicular to the flow. And that's because, indeed, due to its structure, we actually break up large vortical structures into smaller ones that, at maximum, can fit into one of these honeycomb channels. In this module, we've learned about the position of different wind tunnel components and their function and purpose. In the next module, we're going to focus on some measurement and visualization techniques and the main advantages and disadvantages of these techniques. Thank you for watching, and we hope to see you again next time.